okay, at least for this problem, because this is just a dynamic programming problem. In principle, you can use dynamic programming and find out this policy function, right? Just like in your exercise. In your exercise, it is a simple case, the simplest possible case. You have 20 states, right? The size of the tree, 1, 2, 3, 4, up to 20, okay? And then the policy function is that, so for each value of the states, what you are going to do, right? In your tree cutting problem, there are only two choices: keep the tree or cut the tree. However, in this kind of problem, it's much more complicated. You see, this consumption is a continuum value, right? So it's no longer a two discrete choice. Similarly, for KT is a continuum of value. So if you want to use dynamic programming to solve this kind of problem, you have to take a approximation. Suppose you take, let's say, you confine your attention to consumption between 0 to 1,000, let's say, and then you will discretize your control space. Okay, so you consider CT takes the value of 1, 2, 3, 4, 5 up to 1,000, or maybe you want to have a better approximation, then you need to take even more points, right? 0.5, 1, 1.5, 2, and so on. So presumably, if computational cost is not a concern, you should be able to get very good, very accurate solution if there's no computational cost. Now you can imagine if you use dynamic programming, in order to get good approximation of these functions, you need to take many points in your state space, right? Because all these are continuous variable, right? So this KT can take anything between 0 to certain value. ZT is from minus something to positive something, right? So in order to take, so in principle, you can do dynamic programming, but just too difficult to do. And moreover, if it is pure numerical, okay, suppose there's no computational problem. You take, let's say, you take 10,000 possible values, these 10,000 possible values, so that you have a grid 10,000 by 10,000. You run your computer, the solution looks like a phone book, right? A whole bunch of numbers, all a number. It's very hard to understand the property of the solution. Okay, so nowadays, so it turns out that we come up with approximate solution. So you see here, because the policy function is meant to be some function of KT minus 1 and CT, right? And we know that polynomial can approximate pretty much all function, right? So you take the order of polynomial, first order, second order, third order, and so on and so forth, right? So the minimum you can do is to say, okay, suppose you use the linear approximation. You assume that this policy function, they are linear in KT minus 1 and CT. So this is known as a linear solution, okay? And we can do quadratic without any problem, and in fact higher order solution, just more computational, okay? Just more computation. So here we have user-friendly software to do the linear solution, okay? Here notice that this Euler's equation, you see this CT plus 1, you see the T minus 1 and so on. So this thing is without the ET, okay, if you have a problem without the ET, it is a difference equation. Okay, so this is known as the difference equation system. So you have two variables, K and C, and then they follow this relationship. So the solution is a sequence. You want to find those sequence that satisfy this. Now, once you have the ET here, this thing is random. So this CT, KT, they all depends on this ZT here. This ZT itself is random, and this policy functions. So this is known as a rational expectation model. Okay, so this system, how do you solve it? Now, it turns out for linear system, there's well-established method to solve it. Okay, so by a linear system, we mean like the other lecture notes, Lubeck, Professor Lubeck's lecture notes. So this is so Professor Lubeck's lecture notes. We got this thing here. Yeah, this one. Okay, solving linear rational expectation model. So basically, the example I just showed you. Now, in all of our model, we have a set of equation that involve yt plus 1, ct plus 1, and so on and so forth. And then there's an ET like that, but then they may not be linear, like our example that we show you, right? So there's some ratio and so on, so non-linear. So basically the strategy of getting linear solution is that first try to understand in the linear case, we have well-established method. And then we try to linearize the non-linear system and then apply linear solution method. Okay, so this is the strategy for obtaining linear solution. So first you need to understand if you have a linear system like that, how the solution works. So in this handout, Professor Lubeck motivate the solution by a single equation. Okay, so in our neoclassical growth model, we have C and K, right? So it's a two equation system, but try to understand the idea. Suppose you have a one variable, okay? So just one endogenous variable, yt, and then it sort of follow this kind of thing. So this is a first order difference equation, but then there's an ET here, okay? Just like our Euler's equation. And then this ZT is like our TFP, okay? So this is called a forcing process. It exogenous stochastic process. So this ZT is our TFP follow a known AR1 process, okay? Now for these very simple difference equations, first you have to kind of understand what kind of solution you want, okay? So normally we want a stable solution. Namely, the solution is that the YT, okay, so the YT sequence that satisfies this relationship is non-explosive. It won't go to infinity or minus infinity, okay? It is a stationary process, okay? So here, whether the solution will be stationary. So here, let's say this exogenous process, we assume it to be stationary. Like our TFP, we assume it is a stationary AR1. So it won't go to infinity. over time, okay? However, even though this ZT is stationary, there's no guarantee your YT, okay? Your YT that satisfies this relationship must be stationary. In fact, it depends on this coefficient A, okay? Depends on the coefficient A, and for a very simple reason, if you do repeated substitution, okay? So like what happened here, let's say YT plus 1, right? So you substitute, because that equation is meant to be true for all t, right? So YT plus 1 would be A, ET plus 1, YT plus 2, and so on. So you do repeated substitutions, okay? So you will get something like, so you keep doing this kind of thing and then use the law of iterative expectations, you will get this relationship. So after many substitutions, you will get that, okay? Many steps later. And then obviously this sum, okay, when you if you do this repeated substitution for many periods, and then you ask the question, what's going to happen to this right-hand side? Okay, so you take the limit, the cap t goes to infinity, and if your A, okay, if your A is bigger than 1, so you see this term here. Okay, so if your A is bigger than 1, because you raise to very high power, right? So that this term will go to infinity, right? Like if your A is 2, you do 2 times 2 times 2 times 2 and so on, right? Then must be infinity, okay? So so basically, this will be, in this case then, the solution YT will be non-stationary, right? So this is not the solution you want, okay? And on the other hand, if your A is smaller than 1, this will be the solution, okay? So if your A is smaller than 1, this term will go to 0, and then this sum will also be finite. Okay? So for example, suppose your set T is a AR1. Okay, so let's calculate. We can do some calculation here. Yeah, so maybe I use one left-hand side, PC. So let's say this on the other side. On the other side, you can actually come up with a nice solution if your A is smaller than 1. Okay, so if you look at that thing, first of all, these things will go to 0, right? So the A is smaller than 1 because you raise to higher and higher power, right? So the things will go to 0. And what about this term? So we can get a expression for this term if your ZT follows a nice process. So for example, suppose your ZT is an AR1 process. Let's say an AR1 process like that. We can get closed form solution. Okay, so this epsilon t is IID, zero mean, and finite variance. Okay, so AR1 process, we have closed form solution for the forecast. So if you forecast one step ahead, okay, so if you use, this is your forecast, conditional mean, you use this as a forecast. For AR1, we have this closed form expressions, one step, and then for 2 steps ahead, you have this close to the square, and so on and so forth, okay? So very nice closed form solution for AR1. So if you use this formula, so you will see this term can be because this is J step ahead forecast, right? So you plug in the formula there, this should be a row to the power J, right? Okay, so you will get something like, so here this infinite sum will be in a nice, you have a very nice closed form solution. So here these things. This thing should be just A to the J and then row to the J, right? Row to the J. And then here this is stationary AR1, right? So this row is also smaller than 1. Okay? So we assume this A is smaller than 1, rho is smaller than 1. So the product is smaller than 1. And we know we have closed form solution for this case. Okay? For this geometric series, closed form solution. Because the product A times rho is smaller than 1. So we know this sum should be convergence. Okay? So the solution so once you have these things, solution would be yt equals to b times these things, 1 minus a rho, rho to the ct. Okay, sorry. So the forecast, right? So you base on at time t, you want to forecast ct plus 1. Then the forecast should be just the rho times ct, and then 2 steps ahead, then just rho squared times ct, what you currently observe. So you got something like a ct here, okay? So with the ct, okay? So you will get something like this. So yt will be this coefficient times ct. Okay? So this is the solution. This will be the solution of the difference, expectational difference equation. Okay? So you have these things. Okay, so you have these things. Right? You want to find a solution, so your yt should be some function of this set t. Okay, and then that satisfies this thing by construction. Now you can check that this must work. So let me write it down. So this is your equations. And then we say these things follow AR1 process, right? So we say this for AR1, we assume this for AR1, and this is your expectational difference equations. And then by our method, we know that, so we say this is a solution. Solution is this. Okay, so we say this is a solution. Now, how do I know a solution? I can check, right? Substitute in. So I can, because I want to, so we find out this thing, I say this thing will satisfy this equation. So that substitute left-hand side, right-hand side, right? Then you know. So what is this object? So A times ET YT plus 1. So this will be just plug in here, right? Okay. So you will get all this constant factor out, and then ET CT plus 1, right? Okay. But for AR1, we know how to calculate that. So this one should be A E times 1 minus A rho, and then this one should be rho times C of T, right? By the AR1 forecast rule. Okay. So this right-hand side, we know that this should be just this. Okay. So it is this object, and then you can of course calculate. So you can check that if you do this calculation, you get a one-time cancel, right? So you will have D here, T, right? So this is your right-hand side, okay? And then the left-hand side is just your plane. Left-hand side is YT, right? YT equal to P, YT equal C of T. The same, right? Okay, so we check that. Same thing, right? Okay, so this is indeed a solution. Indeed a solution. And this is a stable solution, right? Stable solution. It won't go to infinity because all these things finite number, and then this is set T fluctuating around 0, right? So AR1 stationary process, it won't go to infinity. Therefore, your YT is also not infinity, right? Okay, so this is a stable solution. So you can see that, what this simple example trying to illustrate is that the solution that you're looking for depends critically on this coefficient, whether it's bigger than 1 or smaller than 1. Okay. So we find that if A is bigger than 1, then no stable solution. A smaller than 1, then you get stable solution. Right? So basically, you have to keep in mind this principle. Okay. So when we try to solve the Euler's equation system, we basically make use of the same principle. Okay. Try to keep those parts. So if you have a system like that, let me check back. Let's see here. Yeah, show you this system like that. So the same intuition apply. Okay, so if you have a system, a two equation system like that, okay, with certain ET things, so C and K, right? So a 2x2 system. So in general, you will have two conditions. Okay, so in the motivating example, you will have the A, and here you will have two eigenvalues of the system, lambda 1 and lambda 2. Okay, so if you have lambda 1, lambda 2 both smaller than 1, then you will have a stable solution. If both are bigger than 1, obviously you will have no stable solution. Now the most interesting case, however, is what about one of them is bigger than 1, the other is smaller than 1? How do you do it? Now this is non-trivial. Okay. Now it turns out that for the kind of problem that we use in macro economics, we normally have this kind of situation. One root bigger than 1, the other root is smaller than 1. So this is called a saddle path property. Saddle path. Now, we actually show you what a saddle path looks like last semester when we talked about the Ramsey model. We have a picture to show that. I probably don't have the file here, so let me see. I want to show you the picture just to remind your memory. It's a very nice way to sort of visualize the things. Yeah, so it should still be there. We have a very nice phase diagram, the Ramsey model, right? So I also use this Ramsey model to motivate. But basically, we have if you kind of check back these things, yeah. These lecture notes. So you see this phase diagram show you the trajectory, right? So the locus or the trajectory of the CT and KT sequence that satisfy the Euler's equation. Okay, so this is the trajectory. See, over time, if you start out from point A at time 1, you're here, time 2, you're here, time 3, you're here, and then go to infinity, you will go to here. So this is known as a trajectory, a locus, right? So a time path, something like a path. So what we show you in this phase diagram is that the only path is this path. So this will give you the solution of the social planning problem. Okay, all other paths will not give you maximum utility. Okay, so even though they satisfy the Euler's equation, but the problem is the transversality. Okay, so the Euler's equation is only a necessary condition for the optimum. Okay, so what this phase diagram tries to show you is that if you take any, so here you can trace out all time path or trajectory that satisfy the two Euler's equation, but only the saddle path will satisfy the transversality conditions. Okay, and sequences on the saddle path, they are the solution to the social planning problem. Okay, because they satisfy the Euler's equation as well as the transversality condition. So here, this is sort of the visual way to see the solution. So basically, you want to find out this saddle path. Okay, find out the saddle path solution. So as you can see here, this thing is because a CDKT sequence, right? Each point on the path is a particular combination of CT and KT, right? CDKT over time and so on. So this is actually, so you can imagine if you can somehow find out a formula for this curve, this would be a function, CT as a function of KT, and which is a solution to the social planning problem. But this is just the policy function. This is what is meant by the solution from dynamic programming. Policy function, right? Your control variable as a function of the state. So this saddle path is in fact the policy function. Okay, so basically the thing is that if you can do dynamic programming, suppose you don't have computational problem, okay? You can find out the saddle path without any problem. The only problem is just computational. Okay? However, as we said, because computation is not costless and also is not easy to understand, just a whole bunch of numbers, right? It's very hard to understand. So here what we want is that somehow we want to find out this saddle path without doing dynamic programming. So this is the challenge. And then basically you want to have, so going back to Professor Lubig's note, so basically the saddle path has the property that it won't explode to infinity. See, from the previous picture, it will, if you travel along the saddle path, it will converge to the steady state, right? So C and K won't explode to the infinity. So basically, you want to have, so this sort of plays the role of the Euler's equation. So you want to find out why this sequence that satisfies the Euler's equation, but at the same time, it also won't explode to infinity. This will give you the saddle path solution. Okay, so and this saddle path thing only happens if you have more than one variable. Okay, like the simple case C and K, right? You have one bigger than one, the other. You have two roots, one bigger than one, the other smaller than one. Okay, so this saddle path solution. So here, what happened is that you want to consider in general, suppose you have a system like that, okay? So so the minimum case is that you have this xt is 2 by 1, the c and k, okay? And then it depends on the lag, and then this TFP, and here you don't see the expectation here. What happened is that you can always define this forecast error and get rid of the expectation. Let me show you. Go back to our example. So here you have this expectation thing, right? And because it's non-linear, then you cannot get rid of it. But if they appears in linear form, like so let me suppose I have already linearized it. So it kind of looks like this. Let me show you this case. Yeah, just as an example, okay? Just as an example how you get rid of the conditional expectation. Now, I may not be 100% accurate, but just kind of illustrate. Let's say, suppose you have a equation like that, and then you have so here you have this conditional expectation. Okay, conditional expectation. You can always define a forecast error. Define forecast error to be the actual minus the conditional expectation. Okay, you see here, I can define a symbol like that, right? So this is not like the forecast error. So this is the forecast. You use conditional mean to forecast. This is the actual value. The difference between the actual and your forecast. This would be forecast error. Right? The mistake that you make, right? So based on time information, you use the conditional mean as your forecast and your prediction of CT plus 1, okay? So if you define like that, obviously, this thing can always be written as correct? Because my eta, this eta is defined to be this. Therefore, this is just CT plus 1 minus ET CT plus 1 sort of cancel out, and then you move it back, you will get back the original, right? So whenever, if you have a linear system like that, okay, so in your Euler's equation, suppose everything is linear, if those conditional expectation terms can always be gotten rid of by introducing this kind of forecast error, by using just based on this simple trick, right? So basically, what happened in the notes is that now, moreover, suppose there's a coefficient. Suppose I change my example a little bit. Suppose a coefficient like this. Let's say a theta z here. Suppose you have a coefficient like that. Then just add back the coefficient, right? Coefficient like that. This would be minus theta z, right? Correct? Because just algebra. Suppose it's not really 1, you have this coefficient theta c there, okay? Then you can always same define and then just theta c times this thing, right? These two things will just to be the same, right? So as long as it is linear, as long as your Euler's equation, your expectational Euler's equation is linear, you can always doing this kind of trick. Okay? Whenever you see a conditional expectation, just create this eta on the other side. So going back to the so here, so let me just create example for you. So here you can, now once you have this, obviously you can kind of let's see here what happened to let's see, I need to so this t plus 1, and you can always just shoot backward 1 period without any problem. So you go back to the computer. So go back to the computer. So here, if you have a set of Euler's equation, and then some of them has this conditional expectation, you use this trick. You create a whole bunch of this eta t, and then you can always sort of put the system like that. They're all linear function, right? So linear function of the xt depends on xt minus 1 and so on and so forth. Okay. So in general, you can imagine, as long as your Euler's equation, they are all linear, you can always map the system into this form. This is known as a canonical form. Okay? And then you try to solve this system, try to get rid of explosive behavior. And first you consider the case that this gamma 0 matrix, so just keep in mind, maybe you can always keep in mind, this is the 2 equation system, just like our simple example. So this xt is actually ct and kt, right? So this is 2 by 2, 2 by 2, everything 2 by 2. So suppose this gamma 0 is invertible.